At circle P, line segment LA and LY are considered to be tangent segments to circle P at the same exterior point L at point of tangencies A and Y respectively. Here, we will be needing to solve the values for X, Y, and Z for this given figure by looking into special relationships by tangent segments formed through the same exterior point and all other necessary details. First, let us try to determine what are the specific concepts signified by each of the variable. Here, X represents this angle here, which is an angle formed by the tangent segment LA and the segment formed by connecting the center of the circle to the same exterior point where the tangent segment is drawn. In short, it's an angle. Second, we need to solve the value of Y, which is represented by the tangent segment LA or AL. And finally, Z is that line segment drawn by connecting the center of circle P towards the same exterior point where the two tangent segments are drawn, specifically termed as point L. So let's start with the measurement of angle X. Notice here that X is an angle outside the given circle, and you cannot use here the concepts of inscribed nor central angles. Also, we cannot use here the concept of an angle formed by a secant and a tangent, since first and foremost, this line here is not drawn as a secant, nor there are no given measurement of arcs for both the smaller and the larger intercepted arcs. What we could use here is the concept of the triangle formed here by radius PA or AP, the tangent segment AL and LA, and that remaining segment connecting the center and the exterior point. We know by triangle angle sum theorem that the sum of the interior angles of any triangle is 180 degrees. So we can anchor on that. But first, we need to understand the angle formed by a tangent segment and a radius. This angle here is automatically 90 degrees or a right angle, meaning this is an angle that is or the tangent segment and the chord are perpendicular to one another. There is a theorem that supports this statement. This is automatically 90 degrees. This would mean that we already have 90 and we already have 45. In short, the measurement of angle X plus the measurement, or let's just say already 45 degrees plus this angle, which is again by theorem 90 degrees. Again, all angles formed by a tangent segment and a diameter or a radius on the same point of tangency is 90. When added, this would result to 180 degrees because that's the triangle angle sum theorem. In short, the measurement of angle X plus this, which is 135 degrees, is equal to 180 degrees. The measurement of angle X is 180 minus 135. You will get a result of 45 degrees. So the measurement of angle X is 45 degrees. By the way, the bottom triangle also will have the same measurement. Here, this is also 45. This would also be 45. But since that's not part of our discussion, we're not going to include that. There's also another theorem representing that. So since this is 45, this is 45, this would mean that this triangle here is called an isosceles triangle. Or better yet, specifically, isosceles right triangle, because it has a right angle here or 90-degree angle. The concept of isosceles right triangle will be used to solve y. Because y is this segment here, tangent segment, which is in specification of a triangle. This is a leg. This is also a leg. And since this is isosceles, okay, by the way, we know this to be isosceles since the base angles are equal, 45, 45. So since this is an isosceles, this would mean the measurement of y is equal to the measurement of radius AP or PA, which is just equal to 6 units as well. This is because our triangle is an isosceles right due to equality of base angles. For equality of angles, we call base angles because they are now isosceles. This is now isosceles triangle. So we are down to our last unknown, which is z. Z here is this side pertaining to this triangle. Z is this side directly opposite the 90-degree angle. In other terms, Z is what we call as the hypotenuse of this triangle. And we are sure for it to be called hypotenuse because we have a 90-degree angle. And hence, we can use here the Pythagorean Theorem, which states that the square of the hypotenuse is equal to the sum of the squares of its legs. In this case, AP or PA, that's 6, and you get the square of it, plus the measurement of AL or Y, or better yet, what we already solved as also 6 units. This would mean that Z squared is equal to 36 plus 36, you will have 72. And when you take the root of both sides, let me extend a little bit here, you have Z square root's property. You'll be using plus minus square root of 72. But we will just only use positive since it's measurement. So we have square root of 72. In lowest terms, square root of 72 is 6 square root of 2. This is the value of Z, being the segment joining the center of circle P towards the exterior point L, where the two tangent segments are drawn. This is 6 square root of 2. Of course, if you have missed it, you could also use the special right triangle here, 45, 45, 90 right triangle, which tells us that if in an isosceles right triangle, the hypotenuse is automatically square root of 2 of any of the legs. So square root of 2 of any of the legs, square root of 2 of 6 being the measurement of the leg. These are the values for x, y, and z, where x is an angle and y and z are both measurements of segments or specifically sides of a triangle.